classes on fundamentals of electrical circuits. Now we go into a little more complex looking but very simple AC networks. Okay, we'll also take a look at the infinite networks or ladder circuits. Okay, so let's start off. Please remember that the concepts will be discussed along with the problems, okay, because the concepts with respect to AC are a little different when compared to the concepts associated with DC. Okay, methodologies too. Okay, so if it's an AC circuit, what I recommend is always to have a look at the source in two aspects. One, of course, is the magnitude, which either is an RMS value or is a maximum value. Here, what is given is a maximum value because it is succeeded by the sinusoidal content. Okay. Next point is to look at what is coming with T. Okay, whatever is coming with T in a sinusoidal waveform gives rise to what is called as omega. Okay, omega is the most important aspect with respect to analysis of a AC network, which makes it easy to solve. Okay, so why is it easy to solve? So first we had a look at the network. We see that there are two parallel structures of pure inductors and pure capacitors. Okay, there are two structures where we have an inductor and a capacitor are parallel together. The rest is all resistance. So we have had a look at the source and the connected load as well also. Now let's read the problem. The circuit shown below, the supply voltage is 10 sine 100 1000 T, where 1000 is the omega component. The peak value, so we need not find out the RMS value, the peak value of the steady state current through the 1 ohm resistor, which is the central piece. Okay, so it might give rise to a feeling that it is Wheatstone. It is not. Okay, let's see what it is. Okay, in amperes is what. Okay, so we have a look at, we use the omega to convert 4 millihenry to 4J4 ohms, and use the same omega to make 250 microfarad as equal to 1 by omega c or minus j by omega c, and so we see that 10 raised to minus 6 comes at the top, so 10 and on the denominator we have 250 as also 1000. Okay, so together it's very clear that that's going to be minus j4. Okay, so when j4 and minus j4 are parallel, no doubt about it, though the numerator is okay, denominator talks about j4 minus j4. Okay, because it is the easiest thing to remember is R1 R2 divided by R1 plus R2. So we have J4 minus J4, okay, which is 0, which means infinite impedance. Or infinite impedance is always reflective of an open circuit. So also for the top parallel circuit, where we have again omega being utilized. First for the inductor to get its impedance as equal to 500 milli into 1000, which is equal to 500 ohms. Okay, and for the capacitor, you notice the 2, which makes it very clear to us that it's going to come on the denominator. So we are going to have again 5. Okay, and what is it? It is 10 raised to 6 divided by 2 into 1000. Okay, so in other words, that's also minus j 500 ohms. Again, parallel together gives rise to an open circuit. So there are two open circuits, and the current released by the 10 sine 1000 T flows through 4 ohms, flows through 1 ohms, and then the subsequent 5 ohms and returns. Or in other words, the total impedance, as is always true, is a simple value of equal to 10. That is 4 m and 5 by 10. So 10 by 10 is equal to 1 is the maximum, and the amplitude of the sinusoidal current that's flowing through the resistive elements only. They don't flow through the inductive and the capacitive components. This problem also, we see a series circuit of pure inductor and capacitor and a parallel circuit of inductor and capacitor, and we see a source being applied and an output voltage also being shown, and there are the resistive components which perhaps do not matter at all, because it is the focus is on the inductor and the capacitor, especially when they happen to be pure and without any resistive components joining them. Okay, so now we have, let's read the problem. In the RLC circuit shown in the figure, the input voltage is given by VIT is equal to 2 cos 200t plus 4 sin 500t. So it's any resistive, inductive, capacitive circuits are going to be linear circuits, which means that you can only the diodes and the transistors etc. make them non-linear. So if it's a linear circuit, no doubt we can apply superposition in reverse. That is, the source can be split up. So we apply first 2 cos 200t and then we apply 4 sin 500t. The advantage is that now the two omega values can be separated and used. Okay, so let's talk about 2 cos 200t being applied, and so let us look at the first series network. Okay, so for the first series network, 0.25 Henry multiplied by 200, that is to get the ohmic value, gives you J50 ohms. Okay, and then we come to the capacitor, where capacitor the capacitor's impedance is given by minus J by omega C. So omega is 500 and the capacitance value is 100 microfarad. So we have 10 raised to 6 divided by 500 into 10, 500 into 100. That's also giving us what is called as what is equal to minus J50 ohms. Okay, so J50 and minus J50 in series. What does it mean? Together they give rise to a short circuit. Whereas when they are parallel, they give rise to an open circuit. When they are in series, it is possible that in most of these kinds of problems, it gives rise to a short circuit. What does it mean? It means that the voltage that is applied, that is the voltage component that is applied at the input terminal, becomes completely available at the output terminal. So 2 cos 200t is available at the output terminal as such, with no distortion whatsoever, because the top branch allows the voltage to be available on the other side. Okay, now let's move on to 4 sin 500t as being applied, and then let us watch the other the parallel branch or the shunt branch. In the shunt branch, using omega as 500, we see that 0.4 into omega gives you J 200 ohms, and the capacitance as a reactance gives you 10 raised to 6 divided by 10 into 500. That's again another minus J 200 ohms. So when J 200 and minus J 200 are parallel, that gives rise to an open circuit. And so if there's an open circuit, no currents flow through that path, and so whatever voltage is given to the input is made again available to the output. And though there's a very small because no currents flow, there's no drop. Okay, so it means that in this network segment, VIT is the same as equal to VOT, and of the 4 answers, we see that B is telling us that the voltage, both the voltage components, that is 2 cos 200t and 4 sin 500t, are available as such on the output side by virtue of the short circuit on the upper path and the open circuit in the shunt path, the series path and the shunt path. So that is one way of addressing such problems. Let's go to another problem. So this is also an AC circuit with several voltages and current sources and impedances as well, with all the components are there. Okay, so let's read the problem and then start analyzing. Okay, I suppose you have noticed that all the voltages and currents have angle 0, and and the inductances and the reactances all have and resistance are all of 1 ohm value. In the circuit shown below, the current through the inductor, that's all that's asked, the current through the inductor. Okay, so the first thing that we notice is always going to be the central part. Okay, of course, analysis is via the outer branches, but the thought process starts from the interior. Okay, so the interior tells us that the central point is at 1 angle 0 with respect to both the outer both the outer points. What does it mean? It means that the outer 2 points, that is, let me call them as A and B. The A and B are at the same potential, or A and B can be that the circuit can be folded such that they can be placed one above the other, such that with respect to AB, now O is going to be at 1 angle 0. Okay, so that is what is shown on the right hand side. And now we are once it's folded, we have 1 ohm resistor in parallel with J1 ohm inductor. Similarly, minus J1 ohm capacitor in parallel with 1 1 ohm resistor. Okay, now we are in a position to look at each of these sources and what they contribute. Okay, so if we are looking at 1 volt source only, the other ampere sources, the ampere sources can be considered as open circuited, because that is the concept of superposition. Okay, so for this particular problem, we are not doing anything. We are just imagining it as folded, and then we are thinking about what does the 1 volt source do when separated from the other two sources. Okay, so the other two sources are open circuited, which means that the 1 volt source has no circuit to allow the currents to flow. So the 1 volt source becomes redundant in that particular sense, in the sense of passing a voltage. Okay, now let's look at the top 1 ampere source. Okay, so the top 1 ampere source, when it's functioning, the source, the voltage source is short, and the bottom 1 ampere source is open. So now this 1 ampere source releases a current which splits into two through the J1 ohm and the 1 ohm resistor, and then returns. Okay, that's all that it can do. It cannot use the bottom circuit because it has no space for returning. Okay, and when you look at the 1 amp source beneath it, the same applies to the bottom circuit. Then nothing happens in the top circuit. So the inductor admits a current only by virtue of the working of the 1 ampere source at the top, and that's given by 1 ampere into 1 ohm divided by 1 plus J is going to give you the current through the inductor. Okay, the current division rule, that is 1 ampere multiplied by the other resistor, which is 1 ohm, divided by 1 plus J. Okay, so that's B. B is the answer. And an important concept that has been imparted is that you can fold the circuits together such that the same potential can be reflected across a set of terminals. Okay, so now we have the fourth problem where a circuit is given where there's an AC source as also a DC source. The AC source is given with a magnitude of 5 pi and omega is equal to 5000, and then we have a 1 kilo ohm resistor, 1 microfarad capacitor, and a 1 millihenry inductor, and a 2 kilo ohm resistor. Okay, so what is the problem? Okay, and VAB is shown with a particular direction. Okay, so let's see, in the circuit shown, the average value of the voltage VAB in steady state condition is what? Okay, again, superposition is what is most applicable in in almost all of these problems. Okay, so let's look at the AC source working alone, in which case the 500 volt source is a short. So now it gives rise to a voltage across the capacitor, just as it does in all cases, but the average value is equal to 0 because the capacitor admits a voltage which is according to the voltage division laws, etc. But then it is an AC voltage, and an AC voltage throughout a wave, if you average it, it's equal to 0. Okay, so the AC voltage contributes to nothing. Okay, to no average value across the capacitor. Regarding the DC, what happens is that the AC source is now a short, but the inductor is also a short, but the capacitor is open. If the capacitor is open, all of the 5 volt becomes available across the 1 microfarad capacitor, and it follows the same and it has to balance this 5 volt. So it follows the same signs that is given in the problem, which is so it is equal to 5 volt. As simple as that. That is, you discard you use superposition. So you see that the AC voltage source results in a voltage across the capacitor, which is based on the voltage division rule, but at the same time it is AC in nature, so the average value is 0, and the 5 volt source results in a voltage across the capacitor which is of equal magnitude as the source and in the direction shown, especially because it acts as an open circuit to DC. Okay. So the same concept perhaps is true for the fifth problem also, where we have an AC source and a DC source and a 1 ohm resistor as also a 1 Henry inductor. So let's see what is the reactance value. For that we need to have the we need to have the omega value of Vt. Okay, so let's read. The circuit shown in the figure has two sources connected in series. The instantaneous voltage of the AC source in volts is given by Vt is equal to 12 sin t. So omega equal to 1 and maximum value is 12. Okay, if the circuit is in steady state, then the RMS value of the current flowing in the. So now this time we are asked for the RMS value. Okay, is what? Okay, so that's the question. So we have two sources now. The AC source, the DC source. Of course, when you are talking about the DC source, the AC source is shorted because it's a voltage source, and the inductor is short. So we have the current as given by 8 by 1. That is the 1 is the only resistance that the 8 volt source. The 8 volt source faces. So we have 8 amps. Okay, that's the DC current, and then we have the AC current as given by the DC source is now shorted, and 12. So let's look at the maximum value first. 12 divided by we have 1 ohm, and there are two 1 ohm values. One is for the resistor, the other is 1 into 1 omega. Okay, so we have so the total impedance is square root of 1 square plus 1 square or square root of 2. Okay, so 12 by root 2 gives you the maximum value, and to get the RMS value, divided by root 2 again. So we have 12 by 2. Okay, so that is 6. So 6 is the RMS value for the AC current, and 8 is the RMS value or DC or the DC current. So square them and add them and take the square root. That is 10 amps is going to be the RMS value of the totality. Okay, so I suppose the same principles have been used. The only difference happens to be that it's not average, but the RMS value. Okay, so now let's move on to the sixth problem. Again, there is an AC source given as 1 sin t. So omega is equal to 1. And so resistor value resistor connected to it, and then we have two branches. One is the 1 farad, 1 Henry in series. So if you give omega to both of them, one will become J1, the other one will become minus J1. That is the capacitor minus J1, the inductor J1. So it's a short. Okay, and then we also have, so the 1 ohm connected in between is shorted. So the total circuit is now only has only the AC source and a 1 ohm resistor, and then it's all a short. So that's how current flows. Okay, so the RMS value of the current in the circuit shown below is, so what is it? It's 1 by 1 divided by root 2. So 1 by root 2 is going to be, B is going to be the answer. Okay, so very simple. Most of these all the three problems are similarly oriented. Okay, now we have what is called as the eighth problem. There's an inductor, there's a capacitor with series resistances for them, and they are across an AC source. Okay, the circuit below is excited by the sinusoidal voltage. The value R in ohms, for which the admittance of the circuit becomes a pure conductance at all frequencies. This is possible only if we have what is called as the circuit terminating in the natural impedance of the circuit, and the natural impedance is always given by square root of L by C. Okay, so there is an L value and a C value. So that is how we get R is equal to square root of root 200, which is what that is 10 into 1.414 or 14.14. So if the resistance, both the resistances are 14.14, whatever be the frequency, the circuit is going to be a pure resistance or conductance. Okay, so the seventh problem, we have 10 cos omega t, 4 ohms, 0.1 millihenry and 1 microfarad. The circuit shown at resonance, the amplitude of the sinusoidal voltage across the capacitance is what? Okay, so we have what is, first of course it means resonance, or we have a resonant frequency, and that is omega equal to resonant frequency as is given by 1 by square root of 1 by root LC, which has been shown here as equal to 10 raised to 5. And then what is the current? Current is, because it's a pure resistance now due to resonance, so 10 divided by 4 is going to be 2.5. 2.5 is going to flow, 2.5 maximum value is going to flow through the inductor or the capacitor, creating the same voltage. So it's easier to multiply 25. Okay, let's go to a different kind of situation altogether. That is the infinite ladder network. Okay, so in the picture, perhaps when you observe first, you will see that the dots at the right end indicate that the ladder extends infinitely. Okay, and what do we have here? If we compare RA and RP, that is the two resistance networks that are shown, it is quite clear that from RA, there is the RA and RB are related in such a manner that 1 ohm in RB is parallel to the remaining portion of RA. Okay, or in other words, it is 1 parallel to RA, or the total combination will have to be 1 RA divided by 1 plus RA. If you look at the answers, you see that this is a part of D, and so this could be true. Okay, so let's read the question. RA and RB are the input resistances of circuits as shown below. As the circuits extend infinitely in the direction shown, which one of the following is true? Okay, of course, the first one is not true because RA is not equal to RB. In fact, RB is going to be less than RA because RA is parallel with 1. Okay, so it's going to be less than 1 rather. So RA and RB are not equal to 0, and RA is not less than RB. RB is less than RA. Okay, so this is one aspect. Let's move to a similar question. The second one, here we see that there is a structure of R resistances, again extending in a ladder manner to infinity. Okay, but at the same time there is one resistor which stands apart, which is at the input itself, which is going to be 2 R ohms. Okay, so perhaps it can be now split into 2, that is R plus the rest. Okay, so let's see how it goes. The equivalent resistance in the infinite ladder network in the figure is RE. Okay, so we have to find out the value of RE by R, which means a numerical value has to be found out. So let's look at how it is derived. Later on you can do it directly without derivation. Okay, so here we set RE as equal to 2R plus the rest, 2R plus R parallel RE, because the rest is going to be RE. Okay, so R parallel RE is talking about the resistance structure that comes later on. Okay, so we have RE equal to 2R plus R parallel RE, so which has been solved subsequently. So it becomes RE minus 2R is equal to R to RE by R plus RE. Okay, so when you solve it out, it seems to be that RE is the same as equal to R into 1 plus root 3. This is more or less always going to be true, and so we have so it's very simple to see that RE by R is equal to 2.732. Okay, but when you address a problem like 11th one, where no calculations are asked, but at the same time some values are given, then let's see if the answers are that is the answers to the MCQs are can be more effectively utilized. Okay, so what do we have here? Again, we have instead of resistances, it's an impedance network. So the opening impedance is J9. Then we have a shunt path of J5 and minus J1 or J4, and then it is repeated. The whole structure is repeated infinitely. That is J9, and then the shunt path of J4, and so on and so forth. Okay, so here I would like to say something else, in the sense that when you have J4 in parallel with something, okay, the whole the value of the parallel structure becomes less than J4. Okay, so in other words, the total ZEQ, if you looked at from the left side, is the same as equal to J9 plus a little less than J4. Okay, so it has to be a little less than J13. So let's see, when we look at the answers, we see that A is the only value which is less as also positive, because it is positive because the inductor it is inductive reactance. Essentially, the predominant portion is inductive reactance. Okay, and the question is also the equivalent impedance ZEQ for the infinite ladder circuit shown in the figure. Okay, I suppose this is more often than not true, and let's extend it further in the 13th problem. Okay, in the 13th problem, we see the infinite ladder as such, and a little more data is given as in the infinite ladder network shown below. If R is equal to 1.235, okay, so the resistor has now assumed a particular value. Okay, then the effective resistance between the points A and B approximately is root 5, which is equal to 2.235. Okay, and the network structure is shown, and as we very well know, the total resistance will have to be now R plus a value less than R. I suppose that is clear. The working out is given below, but at the same time, as was done in the previous problem. Okay, so it is still the same logic applies, but at the same time, let us see if the answers help us. Okay, so we have, so if you look at the network from the left end, you see that it is equal to R plus a value less than R. So R is equal to 1.235, and the value less than 1.235 might be anything between lower than 1.235. So the total has to be near around 2.4 or less or lesser. Okay, so the answer 1 can be removed from consideration. Answer 2, let's see, root 5 is 2.235 minus 1, which is 1.235 by 2, which is again very much smaller than 1.235 in series with a value less than in series with. So it's an addition. Okay. Answer 3 seems to be appropriately good because 1.235 plus a value less than 1.235 could be as small as 0.6 or something like that. So it could add up to 2 ohms. Okay, and then answer 4 is root 3 is 1.732 plus 5 is 6.732 divided by 2. It can never be as high as 3 amps. So just 3 ohms. So from the answers itself, you can guess that answer 3 is correct, and it has been appropriately concluded via the derivation. Okay, so derivation is equivalent to what we have done earlier. Okay, and the final problem is again a network structure. There's only a small difference in the sense that there is a resistor at there are 2 resistors leading off, and then we have 1 ohm, and 1 ohm is going to be in parallel with whatever we have seen so far. Okay, so it's going to be again as before, R equivalent is equal to 2 plus. Okay, so the first 2 resistors need to be considered, and then it is going to be 1 parallel R equivalent. The rest, okay, the rest is the same as what we see from here. This is true for an infinite network. Okay, so the derivation was continued as before. So we have R equivalent minus 2 is equal to R equivalent by 1 plus R equivalent, and then it is solved by cross multiplication and getting a quadratic equation and solving for it. Okay, so this is how we can conclude in the sense that the AC networks are also very simple in the sense that the focus needs to be on the omega value, and the omega value will almost always give you a short circuit when a pure inductor and a pure capacitor are in series, and an open circuit when they are in parallel. But of course the values need to be the same or equal. Okay, that is one thing. Second is, of course, when we are having many both AC and DC together, the average value of voltage as a result of an AC power source will be equal to 0, but the RMS value will not be. And the DC, that is, you can use superposition. Okay, so most of the problems will require superposition because you can use AC separately and DC separately because the network is all going to be linear. Okay, so when you are using DC, the old rules that we talked about earlier apply. That is, the inductor is a short and the capacitor is an open circuit to DC. Okay, and then of course an RMS value of a combination is going to be the square root of the squares of individual RMS values or DC values, okay, added together. So I suppose when we come to the ladder network, please remember there are 2 methods. One is, of course, to dissociate the circuit into 2 components. One is the entry point, the other is the R equivalent that comes subsequently as an infinite network. Okay, and then then from the answers itself, you should realize that the total will be definitely less than whatever will be parallel to whatever it is going to be parallel to. Okay, so with these few words, let's hope that we go to the next module, sub-module, that is, we'll be looking at these network elements separately and in combinations. Thank you.